Let us start today's lecture on soil dynamics. Before we start our lecture today, let us see the possible solution for quiz 1. The quiz 1 has already been taken. So, let us look at the slide. The questions for quiz 1 for our course. Full marks was 100 and duration was 1 hour, and all questions has to be answered. Now, let us move to the third problem. So, this was the third problem. What it said? A single degree of freedom undamped system is subjected to a forced vibration with a constant amplitude harmonic loading of p cosine lambda t. If the system had started vibrating from absolute stationary state, that is, the initial displacement and initial velocity both are 0. Starting from the first principle, derive the expression for the final displacement response of the system, and then draw the displacement response profile for a limiting case when the exciting frequency, that is lambda, approaches the natural frequency of the system. So, let us do this solution starting from our basic principle or first principle. So, the single degree of freedom model undamped system we are drawing now. So, M K, this is our x of t, it is subjected to a forced vibration with p cosine lambda t. So, that is the basic single degree of freedom model given to us. So, what we know, the equation of motion is given as m x double dot plus k x equals to p cosine of lambda t, that is our equation of motion, or x double dot plus omega square x equals to p by m cosine of lambda t, where this omega is root over k by m is natural frequency. Now, to get the solution, x of t is composed of x of t complementary function plus x of t particular integral. To get x of t complementary function, what we do? We equate it with 0. So, we can write down the equation x double dot plus omega square x equals to 0. Now, let us say x t equals to e to the power s t is the form of the solution. So, we can put it in the expression s square e to the power s t plus omega square e to the power s t equals to 0, or s square plus omega square e to the power s t equals to 0. Now, e to the power s t is non-zero, otherwise it will give trivial solution. Therefore, s square is minus omega square. Therefore, two roots of the equation we will get s 1 s 2 as plus minus root over minus omega square, which is nothing but plus minus imaginary number I omega. Therefore, the complete solution, not complete solution, the complementary function that can be expressed as e to the power I omega t times a constant plus another constant e to the power minus I omega t, because plus I omega and minus I omega are the two roots. So, this equation, as you know, we have done earlier also in the class. The solution can be expressed as a cosine of omega t plus b sine of omega t. The same thing we can express. Now, these constants we have to obtain later on, because we have another part of the solution, that is particular integral. So, now to get x of t particular integral, what we do? First, we assume some form of the solution. So, x p of t, let us say is expressed as d cosine of lambda t plus e sine of lambda t, because our given function is a harmonic function. So, that is why the solution we are assuming in the form of the harmonic expression. So, it will give us x double dot t as minus lambda square d cosine of lambda t plus e sine of lambda t. If we put this in our basic equation, which is nothing but this one, that is x double dot plus omega square x equals to p by m cos of lambda t. So, now we are putting this in that equation, we will get minus d lambda square cosine of lambda t minus e lambda square sine of lambda t, that is x double dot plus omega square times x. So, d omega square cosine of lambda t plus e omega square sine of lambda t, that is equals to p by m cosine of lambda t. And what we had learned, that now we can equate the cosine components and sine components on the both sides. So, what we can get if we equate the sine components, it will give us e times omega square minus lambda square equals to 0, which will give us e equals to 0, because this is not equals to 0. Omega is not equals to lambda. And what about the other constant d? For that we will equate the cosine terms. Now, equating cosine terms, we can write d omega square minus lambda square cosine of lambda t equals to p by m. Therefore, d is p by m omega square minus lambda square. So, what is the complete solution? Therefore, x particular integral part is p by m cosine of lambda t by omega square minus lambda square, because e is 0, the other component is not there. Therefore, the total solution x of t is now a cosine omega t plus b sine omega t plus this particular integral p by m cosine of lambda t by omega square minus lambda square. So, that is the complete solution. Now, we have to find out these two constants using our given initial conditions. So, what are the initial conditions given to us? That it starts from absolute stationary state. So, x at t equals to 0 is 0 and x dot at t equals to 0 is also 0. It is given to us. So, now let us differentiate this equation to find out the expression for velocity. So, this is the expression we obtained just now for the total solution of the displacement function. So, x dot t is nothing but, now we are differentiating this, minus a omega sin omega t plus b omega cos omega t. Now, this one will give us minus p lambda by m sin lambda t by omega square minus lambda square. Now, we will put these values here. So, if we do that in this equation first, what we will get if we put the velocity at t equals to 0 is 0, this term vanishes because sin 0, this term remains, it is b omega, this is also sin 0, so vanishes. So, x dot at t equals to 0 will give us only b omega, which will imply b is 0, because omega cannot be 0. So, b is 0, fine. And now, if we put the first condition of displacement equals to 0 at t equals to 0, what we will get? X at t equals to 0 is 0. Let us look at the solution once again. This remains a, this vanishes, this remains p by m omega square minus lambda square, right. So, let us write it. So, A plus p by m cosine of lambda t by omega square minus lambda square, which will give us A as minus p by m cosine of lambda t by omega square minus lambda square. Therefore, the complete solution we can now write it as x of t equals to, sorry, cosine of lambda t will not be there, because it is 1. At t equals to 0, this is 1. Minus p by m 1 by omega square minus lambda square. So, A cosine of omega t was the solution. So, minus p by m cosine of omega t by omega square minus lambda square, plus b is 0. So, that component is not present, and the third component is, so let me take the solution once again. Yes. So, A cosine of omega t. So, A is this part. So, cosine of omega t, b is 0. So, it vanishes and this particular integral part remains. So, plus p by m cosine of lambda t by omega square minus lambda square, or x of t is equals to p by m cosine of lambda t minus cosine of omega t by omega square minus lambda square. So, this is the final solution of first part of this problem number 3. Okay? So, this is the complete final solution of the system. That is what it is asked, that derive the expression for the final displacement response of the system. This is the derivation and expression of the final response, displacement response of the system. Now, what is the next part? In the next part, it is asked also draw the displacement response profile, this profile, not with this function. What is asked? For a limiting case, when this exciting frequency lambda approaches the natural frequency of the system. So, what we can write? It is asked to find out limit of x of t when lambda approaches omega. That will be limit lambda tends to omega p by m cosine of lambda t minus cosine of omega t by omega square minus lambda square. So, when it approaches this one, from our basic concept of limit, what we can derive? This expression gives us p t by 2 lambda m sine of lambda t. So, it becomes actually sine lambda t by 2 lambda when lambda tends to omega. So, this is the final response when it approaches exciting frequency, approaches natural frequency. What does it mean? A kind of resonance condition is going to form. So, I asked you to draw this function with respect to time. So, I wanted to feel you that under a condition close to resonance, what will be the response of the system. So, let us draw this. Now, it is pretty easy to draw this function. Let me put it here. So, T, I am drawing this limiting value of x of t when lambda approaches omega. What happens when t is 0? It starts from 0, and how this equation we can draw easily? This will be, you remember, when there is the two functions and one is multiplication of the other one, sine function is harmonic function and t function is linearly increasing function with a slope of p by 2 lambda m. So, how to draw this very easily? Let me extend this side of the axis also. So, linearly increasing lines I have drawn. The slope of it is nothing but this p by 2 lambda m, right. I am just drawing the equation of y equals to c x, where c is the slope of the line. So, this part I have drawn. Now, there is another function attached to it, which is sine of lambda t. So, the actual response is not this line, but a harmonic function like this. So, can you see what type of disaster it is going to happen? Means when lambda approaches omega, of course, in resonance condition we are going to get maximum displacement. So, that is what it is happening. It's keep on increasing. Actually, this also goes to the next line. So, it follows that envelope. Fine. So, this is the final answer of the problem. Okay. Now, let me move to the last problem of our quiz 1. So, the fourth problem was a machine foundation was supporting a machine with a rotating eccentric mass, which gives the design value of the maximum dynamic magnification factor as 1.2. The machine is now replaced with a new machine for the same foundation to support a machine subjected to a constant harmonic loading. If the frequency ratio and damping ratio remain same for the old and new systems, compute the new dynamic magnification factor and also comment on the force transmissibility ratio of the new system. That is, as a designer, I want you to comment on the whether the new machine installed for the old foundation is safe or not. So, let us start the solution of the fourth problem. What it said, initially the machine foundation was of rotating eccentric mass type, and for that the expression for maximum dynamic magnification factor, which is expressed like x m by m e in our usual terms, that maximum value was 1 by 2 eta root over 1 minus eta square. We had derived these things, we know this one. This value is given to us as 1.2. So, only unknown is eta. So, solving this, we can get eta, two values we are getting, one is 0.88, another value is 0.469, and imaginary values are not considered. Of course, as you know, the damping ratio cannot be imaginary. Now, from this, again the value of eta equals to 0.88, that will not give a maximum DMF, because in the previous lecture what we have understood, if eta is greater than 0.7, it always keeps on giving a no magnification as such. So, the chosen design value of eta is 0.469. So, this is our design value given to us. Now, where this maximum DMF occurs for a rotating mass type system machine, it occurs at frequency ratio r equals to 1 by root over 1 minus 2 eta square. Fine. Now, we know this is our design value of eta. So, put it here, we will get the frequency ratio as 1.34. So, this was our old system. Now, what is done? The machine is changed, but foundation remains same. Now, the new machine is subjected to constant force type harmonic loading, but for the system the damping ratio and frequency ratio is maintained as same as the previous case of old system. So, these two values remain same. It is asked what will be the dynamic magnification factor for the new system. So, DMF for the new system which is subjected to harmonic loading with constant amplitude, that is given by 1 by root over 1 minus r square whole square plus 2 eta r whole square. Now, we have already computed r is 1.34 and eta is 0.469 because they remain same. So, just put these values, we will get the DMF of the new system. It is of course not the maximum, because in earlier case where the maximum occurs, for this case it is not the point where the maximum occurs. Okay. So, this is the solution of first part. That is what it is asked, that what is the new dynamic magnification factor, and the last part says the transmissibility ratio, force transmissibility ratio, that T r is given by root over 1 minus 1 plus 2 eta r whole square by root over 1 minus r square whole square plus 2 eta r whole square. That is the expression for transmissibility ratio. Now, eta is known, r is known, you put these values, we will get it is coming as 0.13, which is much lower than 1. So, as a designer I asked you to comment on this. So, the new system will be very safe, because it is transmitting much lower force than what it is subjected to the foundation. So, our foundation will be very much safe in the new condition also. So, that the comment you should provide as a designer at the end of this problem. Fine. So, with this we have come to the end of the solutions for this quiz 1. Now, we will start our today's lecture with module 2 on vibration theory. A quick recap of what we have learned in the previous lecture. We have seen for any arbitrary excitation how we can compute the solution using the concept of Duhamel's integral if it starts from absolute stationary state. It is similar to the concept of derivation for the impact loading, but it is considered in small infinitesimal strips and then integrating over the entire time for which the excitation is working, we can get the complete response of the system. Then we have seen the case of dynamic loading coming due to the taxing of vehicles on uneven guideways, when a vehicle is moving at a constant velocity v and there is undulations on the ground, then the distance travelled at a time t we have computed, and then the final solution we have seen in this form, which can be easily obtained depending on the profile of the ground, which we have assumed as a harmonic profile. Then we have seen vibration isolation. There are two types of vibration isolation, force isolation and displacement isolation, and where are their applications? Practical application of force isolation in case of machine foundations. We want to make our foundation safe with respect to the applied load to the machine, and the displacement isolation, the practical application in terms of structure subjected to say earthquake loading, where the earthquake comes to the ground level and the applied displacement due to the earthquake should not be transferred or magnify at our superstructure level. So, that is why we want to protect our superstructure. So, that is the concept of using displacement isolation. Then we have derived the expression for force isolation, from which the expression of force transmitted to the foundation to the force amplitude of force applied to the machine was obtained, and the expression is nothing but exactly as transmissibility ratio. So, we termed it as force transmissibility ratio, which varies with respect to different frequency ratio and different damping ratio of the system like this. And we have seen that the value of R greater than √2 will always give us the transmissibility ratio, force transmissibility ratio less than 1, which is desirable for the system as a designer. Similarly, the displacement isolation we have seen, if the displacement function for the ground displacement is considered as a harmonic like this, the transmissibility ratio can be expressed in the same form of the force transmissibility ratio, the expression remains same, and that is why the distribution also remains same with respect to the frequency ratio and for different damping ratio values. Then we have seen how the vibration measuring instruments are designed to measure the vibrations of the ground, and the measurement of displacement can be carried out, and this also varies a profile with respect to different frequency ratio, and for a value eta greater than 0.7, whatever be the value of R, we have seen this magnitude will be always less than 1. Now, coming to today's lecture, we are starting with a new subtopic, multi-degree of freedom system, basic equation of motion we want to formulate for a multi-degree of freedom system. So, let us do the derivation for the basic multi-degree of freedom system, how we can address this problem. So, let us draw a multi-degree of freedom system here first. This is mass M1, damper and spring K1, damper C1, then mass M2, mass M2, damper C2, spring K2, then mass M3, mass M3, damper C3, spring K3, and this is the fixed end. Now, what are the degrees of freedom of this system? This is x1t, this is x2t, this is x3t. So, I have drawn a system with 3 degrees of freedom, x1, x2 and x3. And to this, the forces applied are externally dynamic load applied are F1t on this first mass, F2t on this second mass M2 and F3t on this third mass M3. So, these are the externally applied dynamic load on the system. So, this multi-degree of freedom system, now if we want to derive the equation of motion for this basic system, what we need to do? The first thing, to draw the free body diagram of each component, that is for each mass. Now, we will draw the free body diagram. So, let us do that. Free body diagram for the first mass will be this is M1, it is subjected to F1t as externally applied dynamic load. Now, x1t I have given at one particular instant of time in this direction. So, the forces of resistance will come and it will act like this. F I will be m I x1 double dot This is inertia force. Then there will be a spring force and a damper force. Now, how much will be the spring force? Spring force should be K1 times the relative displacement between this mass and this mass. So, x1 minus x2, and the damper force should be c times relative velocity between these two mass. So, x1 dot minus x2 dot. So, these are the forces acting for the first mass. So, this is FBD of mass m1. Now, if we want to draw the free body diagram of the second mass m2, what it should be? For m2, it is subjected to externally applied dynamic load F2T. Now, x2 is in this direction at one particular instant of time, vertically upward we have taken. So, inertia force will be m2 x2 double dot in this direction. And what are the spring forces? This spring force and this damper force. This spring force should be K2 times, let us look at here once again, this spring force K2 times relative displacement between these two masses, and the damper force will be C2 times the relative velocity between these two masses. So, K2 times x2 minus x3, and this damper force is C2 times x2 dot minus x3 dot. Is there any other force? Yes, because to maintain the internal equilibrium of these two systems, whatever forces are acting from this mass m1 to mass m2 connected through this damper and spring, that equilibrium, internal equilibrium has to be maintained. So, whatever this damper force and spring forces are acting in this direction, downward direction, the same magnitude forces must act in upward direction to maintain the internal equilibrium of the system. Fine. So, what will act here? We will have this K1 times x1 minus x2 and this is C1. So, C1 times x1 dot minus x2 dot. So, this completes the free body diagram of mass m2. Now, the third mass, that is mass m3, if we want to draw the free body diagram, what are the forces acting on it? The externally applied dynamic load is F3T. On this side, we will have m3 x3 double dot as the inertia force, because again we have taken at one instant the direction of movement like this. So, inertia force in this direction, and spring force, damper force connected because of this K3 and C3. Now, they are connected to a fixed support. So, there is no relative displacement between x3 and nothing is there. So, it should be K3 times x3 and this should be C3 times x3 dot. Any other force? Yes. We have to now maintain again the internal equilibrium between this mass m2 and m3, right. So, whatever these forces C2 x2 dot minus x3 dot and K2 x2 dot minus x3 dot were acting on mass 2 in downward direction, the same force in opposite direction must act to maintain the internal equilibrium because of the connectivity through this C2 and K2. Clear? So, we will have here K2 x2 minus x3 and here C2 x2 dot minus x3 dot. So, that completes the FBD of mass M3. So, is it clear now how the free body diagram of each of the masses we have drawn? Now, from this free body diagram, what we have to do? We have to use now D'Alembert's principle. So, now let us use the D'Alembert's principle for each of these free body diagram, that is equilibrium conditions we will consider for each of these masses. And what we can write from FBD of mass M1, which is expressed here or shown here. So, using D'Alembert's principle, we can write M1 x1 double dot in this direction plus C1 x1 dot minus x2 dot plus K1 x1 minus x2. This is equals to F1 of t. This is first equation we got using D'Alembert's principle for this free body diagram of mass M1. Now, let us use the free body diagram of mass M2. So, free body diagram of mass M2 is here now with us. What we can write? M2 x2 double dot plus C2 x2 dot minus x3 dot plus C1 x2 dot minus x1 dot plus K2 x2 dot minus x3 dot K2 into x2 minus x3 plus K1 x2 minus x1 equals to F2 t. So, this is the second equation. Do you agree with me? What I have done, this one is in the upward direction, this is downward. So, I made it downward by using x2 dot minus x1 dot. Similarly, this also I made it downward K1 x2 minus x1. So, that is why all these terms I have taken in one side and the externally applied force I have taken on the other side. Now, from the free body diagram of the third mass, we can use the D'Alembert's principle and write the equation like M3 x3 double dot plus C3 x3 dot plus C2 x3 dot minus x2 dot plus K3 x3 plus K2 x3 minus x2 equals to F3 t. That is the third equation. Here also what we have done, these two forces were acting upward, we make it downward by just changing the sign x3 dot minus x2 dot and x3 minus x2. So, that is why we have taken everything on this side, and these are the three governing equations we are getting using D'Alembert's principle for each of the three masses. Now, if this entire set of equations we want to put in a simplified form, what we can use? We can use the matrix form, then we can represent these equations in a better way or in a easier way. So, let us put these equations in the matrix form and let us see how it will look like in the matrix form. I have M1, M2, M3, 0, 0, 0, 0, 0, 0. With this, the vector is acceleration vector x1 double dot, x2 double dot, x3 double dot. Then I have the next matrix C1 minus C1 0 minus C1, C1 plus C2 minus C2, 0 minus C2, C2 plus C3, and associated vector is velocity vector x1 dot, x2 dot, x3 dot plus k1 minus k1 0 minus k1, k1 plus k2 minus k2 0 minus k2, k2 plus k3, and associated vector is displacement vector x1, x2, x3, which is equals to the externally applied dynamic load vector F1t, F2t and F3t. So, you can see these are nothing but the same equations 1, 2 and 3 we have written in the matrix form. Okay? So, in other words, we can simply write it as m x double dot plus c x dot plus k x equals to f of t. What does it mean? Even for multi-degree of freedom system, the basic governing equation of motion, the form of basic governing equation of motion remains same. That is mass times acceleration, damper times velocity plus spring constant times displacement equals to applied dynamic load. Whatever we have seen in the single degree of freedom system, the same equation is valid for multi degree of freedom system. Only change is for single degree of freedom system, these were just a single quantity or values. Now, for multi degree of freedom system, these are the matrices, that is, this is mass matrix, this is damper matrix, this is stiffness matrix, and for single degree of freedom system, this acceleration, velocity and displacement were just again a single parameter. In this case, these are the vectors: acceleration vector, velocity vector and displacement vector. Also, this right hand side earlier was a single force, single value force. In this case, it is a force vector for number of degrees of freedom. So, suppose if you have a 2 degree of freedom system, what should be the size of mass matrix? 2 by 2. Size of this damper matrix 2 by 2. Size of this stiffness matrix 2 by 2 and size of this acceleration vector 2 by 1. Size of this velocity vector 2 by 1. Size of this displacement vector 2 by 1, size of this force vector 2 by 1. So, for n numbers of degrees of freedom of a system, we will have mass matrix with n by n, damper matrix n by n, stiffness matrix also n by n, whereas the acceleration vector will be a vector of n by 1. This velocity vector will be a vector of n by 1 and displacement vector will be n by 1. Similarly, the applied dynamic load vector will be of size n by 1. So, this is the general form of the equation or governing equation of motion for a multi degree of freedom system. Now, in this case, what you have seen, all the matrices this matrix what you have seen, it is perfectly diagonal. In this case, these are also symmetric matrix. About diagonal, they are symmetric. Both damper matrix, stiffness matrix, mass matrix, and this is absolute diagonal, other elements are 0, other entries are 0. So, let us see whether this is the always case or not. Let us take one example through which we will show the effect of coupling of different parameters, and if the different parameters are coupled, what we need to do to get the solution. So, effect of coupling we are considering for different parameters. Let us take a simple problem of a rigid beam with varied cross sectional area, which is having a mass of capital M, attached to two springs, say K1 and K2. I am considering initially just an undamped system to show you the effect of coupling, and say this is the CG of the beam. So, this is center of gravity, and the distance of this center of gravity from these two ends are, say, capital L1, capital L2, and the total length of this beam is capital L. Now, these two springs are connected in such a way that the elastic center of the system is here. So, this point is EC. What is EC? Elastic center. How elastic center is defined? Elastic center is such that, let us say, from two ends the distances are, this is small L1, this is small L2. So, elastic center is such that K1 L1 is equals to K2 L2 at that point. So, that is the definition of the elastic center. Now, we will see that for this system, a 2 degree of freedom system, we are considering both rotation and displacement of the system. So, both rotation and displacement of the system we are considering for this, which is giving us a 2 degree of freedom system. Now, selection of the axis for the rotation is extremely important. Why? Let us see. What I said, the selection about which this beam will rotate, the axis will rotate, is extremely important for this problem to know the effect of coupling. Why it is so? Let us see. So, we can assume, so choice of coordinate system, what we say this as choice of coordinate system with respect to the rotation of the beam. We are considering different cases. The first case I am considering when the rotational axis passes through the center of gravity of the system. What does it mean? If I just draw it like this, what I want to say, the line diagram I am drawing, it has rotated about its CG. So, about CG its rotation is angle is theta. So, this is the center of gravity. So, what has happened, the 2 degrees of freedom for this beam I am considering, it has displaced vertically down at a particular instant So, this is the direction of motion I am considering. It has displaced as well as it has rotated. And for that rotation, we are considering it has rotated about its center of gravity. So, this is the case I am considering here. So, what will be the free body diagram for this system? If I draw the line diagram, so this was the location of our CG earlier. Now, the beam has moved to a new position like this, and it has rotated about this CG, and that angle of rotation we are considering as theta. So, it has moved down as well as it has rotated about the center of gravity. What are the forces should come on the system? At CG, we will get, suppose if the vertical movement up to this point CG is y, then there will be a vertical inertia force m y double dot acting at the CG because of its vertical movement. Also it has rotated. So, there will be a rotational inertia force also, which will try to put it back to its original position. So, I theta double dot in this direction, so that it goes back to its position. Now, two springs are connected at these two ends. Spring forces will act. What will be the spring force at this end? It will be vertically upward because it goes back to its original position. Try to, so K2 times, what is the displacement for this spring? That is y plus L2 times theta. Am I right? Because see the distances, L2 is from CG to this end. So, L2 times theta, fine, and this side it is L1 times theta. So, this distance is L2 and this distance is L1. And another spring force that also will act vertically upward, because see final displacement of this point is downward. So, it will again try to put it up. So, it will be K1 times y minus L1 theta. Okay? This free body diagram is clear. So, if these are the forces, now what we can do? We can write down the moment equilibrium about the CG. So, if we write the moment equilibrium about CG, what we should get? So, sum of moment about that CG should be equals to 0. So, let us put it here, so that we can see all the forces. Anti-clockwise I theta double dot. So, I theta double dot. This m y double dot is not creating any moment about the CG. What else it is creating? This is also creating anti-clockwise. So, K2 L2 y plus L2 theta, and this is creating clockwise moment. So, minus K1 L1 y minus L1 theta equals to 0. And another equation we can use, which is sum of vertical forces equals to 0 for the system, which will give us m y double dot vertically upward. This is also vertically upward, vertically upward. So, plus K1 y minus L1 theta plus K2 y plus L2 theta equals to 0. So, these two equations we got, which can help us to get the 2 degrees of freedom solution, that is in terms of y and theta. Those are the 2 degrees of freedom, right? Vertical displacement and rotation. So, this one we can represent it in matrix form very easily. m 0 0 I, then the acceleration vector y double dot theta double dot plus k 1 plus k 2, then k 2 L 2 minus k 1 L 1, then k 2 L 2 minus k 1 L 1, then k 2 L 2 square plus k 1 L 1 square times y and theta equals to 0. We considered the free vibration case. So, this is our mass matrix, this is stiffness matrix. You can see mass matrix is diagonal symmetric, stiffness matrix is symmetric. About this, these two are same elements, but it is coupled. Can you follow? These two gives us these two equations. See m y double dot, then with theta nothing is there, k 1 y plus k 2 y, then this one k 1 minus k 1 L 1 theta plus k 2 L 2 theta equals to 0. This is this equation, and the second one is 0 with this I theta double dot, then this one is k 2 L 2 y minus k 1 L 1 y plus k 2 L 2 square k 2 L 2 square theta, this gives k 1 L 1 square theta equals to 0. Okay. So, with this we have seen for this case mass matrix is uncoupled, whereas the stiffness matrix is coupled. Okay. Now, we can consider the other cases with different center for the rotation. That is, for the first case we have considered the CG as the point of rotation. Now, if we take any other point, say elastic center as point of rotation, what should be our equation of motion? And then we will see any other point, say any corner of the beam we have taken point of rotation, then what should be the equation of motion. So, this depends on the choice of the coordinate system, that we will see in the next lecture.